In this video, you will learn about the relationship between pressure, volume, temperature, and a quantity of gas. And you will also learn how to use the ideal gas law to solve for an unknown variable. So let's use this PhET simulation to explore the ideal gas law. And what we're going to do here is we're going to look at how different variables affect the pressure of our gas. Okay, so if you remember, pressure is really just the force divided by the area, right? And if we think about what's causing that force, the force is created when these particles strike the edge of our container, right? And that container has to re-exert a force back in order for that particle to maintain its energy. So remember, this is an ideal gas, so that means that our collisions here are all elastic, so kinetic energy is conserved. So right now we're holding pretty steady at between 500-600 kilopascals. Okay, so let's see what happens when we adjust the volume of our container. So what I'm going to do is I'm going to decrease the volume here, and we're going to see what happens. So as I decrease the volume, you can see that our pressure increased fairly dramatically, right? Well, let's think about why that is. If we look at what pressure is, again, pressure is equal to force over area, okay? So right now we have these particles exerting force over a smaller area. So as area gets smaller, pressure gets bigger, okay? Pressure gets bigger. So let's go ahead and expand that out again. Okay, so now let's look at how temperature can affect pressure. So what I'm going to do is I'm going to add some heat here. So as the temperature increases, let's observe how that affects the pressure. So you can see that as I'm adding the heat there, the pressure is increasing pretty dramatically, right? So let's go ahead and settle that down. So at 564 Kelvin, right, our pressure here is around 1100, 1200 kilopascal. So as we increase the temperature, we increase the pressure. And think about why that is, right? Remember, temperature is the average kinetic energy of a gas. Okay, and so as we're adding temperature, we are increasing the average kinetic energy of this gas. And if you think about kinetic energy is the energy of motion, right? We back in AP Physics 1 or in Physics 1, we discussed how kinetic energy is just 1/2 mass times velocity squared. Well, it's really no different here. As the velocity increases, so does the energy, right? So as we add energy to our system, right, we're going to get we're going to get more collisions, and we're also going to get faster collisions, right? So the force required to bounce those particles back is going to increase, and that's going to increase our pressure. Remember, pressure is equal to force over area. So increasing temperature increases pressure as well, right? And it's really because these little particles are striking the container more forcefully and more frequently, okay? So let's look at what happens if we increase the number of particles, right? Let's look at what happens if we increase the number of particles. So what I'm going to do is I'm going to bring this back down a little bit. Let's bring that back down. Okay, there we go. That's good. And then let's go ahead and put some more particles in there, right? And I want you to watch what happens when we put more particles in there. So right now we're at about 750 kilopascals. Roughly, let's see what happens when we add more. So when we're at 50 particles, let's increase it to 100. And wow, look at that. Our pressure essentially doubled, right? Our pressure essentially doubled. So let's think again about what's happening here microscopically, right? So as we introduce more particles into our gas or into our container, okay, we doubled the number of particles. We're getting a lot more collisions against the container. So a lot more collisions means a lot more force and over the same area. So we're going to increase our pressure, okay? So let's look and see again what happens if we increase the area that these particles have to collide over, right? So if we increase the area of our container, increase the volume, I should say, the volume of our container. So if we increase that, right, pull that out there, we can see that our pressure drops pretty dramatically, right? So again, we have the same we have the same energy here, right? But it's dispersed over a wider volume. And that means that we're going to have a lower pressure. Remember, pressure is equal to force over area. If area increases, we're going to have a lower pressure. Okay, let's bring that back. Okay, so now let's look at what happens when we hold volume constant. Okay, we hold volume constant. Okay, and then we increase the heat here. Okay, you can see our temperature rises dramatically, as does our pressure. Okay, but what happens if we were to hold pressure constant and then increase our temperature here? What do you think would happen there? Well, let's look. So as we add heat to our system, okay, and we hold pressure constant, okay, our volume gets greater. All right. So our pressure was held constant, but what we did was we added heat to our system while keeping volume changeable. And what that did was that it increased the volume of our container. Okay. And then finally, let's look at what happens when we hold temperature constant while adjusting pressure. So if we, holding pressure constant while keeping temperature constant as well. So if I move that there, right, I have to lower my temperature, right? So if my temperature is adjustable, I have to lower my temperature if I want to maintain my pressure at a smaller volume. Okay, so I had to lower my temperature. Likewise, if I increase my volume and I want to maintain that high pressure, I have to add heat to the system. Okay, so hopefully you're kind of seeing the relationship here. But let's go ahead and kind of codify that relationship in an equation that we can use. All right, so now that we've looked at the ideal gas law simulation and we've kind of identified some relationships, let's try to put this into an equation. So as we've seen, we know that based on the simulation that if we had these 4 different variables to consider when talking about a gas, right? So the pressure of the gas, the temperature of the gas, the volume of the gas, and the number of particles that make up that gas, or the number of moles. Remember, moles. If you've taken chemistry, you should know moles already. But a mole is just another way to identify the number of something. Okay, we'll talk more about that in a minute. So let's say that we're going to look at the effect that each of these variables had on the pressure of our gas, right? So if you remember, volume, okay, if we decreased the volume, what happened to our pressure? Well, in our little simulator there, if we decrease the volume, our pressure went up, right? If everything else stayed the same. So if temperature and number of particles stayed the same, if our volume decreases, our pressure increases, right? So we're just going to say that as our volume decreases, okay, pressure increases, right? So as volume decreases, pressure increases, and vice versa, right? If volume increases, then pressure will decrease, okay? Let's look at temperature, right? Let's say we increase the temperature of our gas, right? And volume remains the same, and the number of particles remains the same. If we increase the temperature of our gas, what effect does that have? Okay, we increase the temperature. Well, if you remember, if we increase the temperature, okay, that increased the average kinetic energy of the gas, which created more force against the container wall. Remember, more force over the same area, we're going to increase our pressure, right? So pressure increases as temperature increases. Again, assuming that we have a fixed volume and a fixed number of particles, okay? And so what happened when the number of particles increased in our container? So as we added as we added gas molecules or gas atoms, whatever, to our container, what happened to the pressure? Well, the pressure also increased. Okay, remember we had more particles in there. Again, assuming the same temperature and volume, adding more particles will increase the number of collisions. It'll increase the force against the container. It'll increase the force the container has to press in on. So larger force over a smaller area, or over the same area, we increase our pressure. All right. So let's look at an equation. Let's look at an equation that we can use to kind of put all this together, right? So we said that that pressure, okay, pressure is is proportional to temperature, right? And it's proportional to the number of particles in the gas, okay, or the moles of gas. So let's just say that pressure then, so P, all right, and then let's put an equal sign over here, okay. We're going to say that so P is pressure, obviously, but we haven't really talked about the number of particles, what variable we're going to use for that. And there's actually two variables that we can use. One is for the number of particles, the other is for the number of moles. So we're going to start off by talking about the number of moles first, and then I'm going to show you a different equation that you can use if you're given the number of particles. Okay, it's really the same equation. It's just a little bit different based off of whether or not using number of particles or number of moles. Okay, so we know that it's proportional to the. So we're going to start off with particles. We know it's proportional to the number of number of moles. We know it's proportional to the number of moles. So I'm going to say P is equal to N. Okay. And then the next thing we're going to add in there is a variation on Boltzmann's constant. So if you remember Boltzmann's constant from a previous video, that was our K value. Well, now we're going to look at the ideal gas constant, which is symbolized with the letter R. Okay, so the ideal gas constant is symbolized with the letter R. So P, and then put an R there. Okay. And then what else is pressure directly proportional with? So we look at that and it says temperature, right? So P and then temperature. Okay. And then also volume. Okay, volume has a relationship with pressure as well, but volume has the opposite relationship with pressure, right? So as pressure increases, volume decreases, or vice versa, right? As volume decreases, pressure increases, or as volume increases, pressure decreases. So what that means is that P is equal to nRT divided by V. Now, that's certainly one way to write it. Okay, we can do that. But the most common way that it is written is P times V is equal to nRT, right? And that's pretty much the ideal gas law right there. Like I said, you can rearrange this equation any way you want to, really. But let's go ahead and identify our different variables, right? So N in this case, N is the number of moles of gas. Right? So if you remember from chemistry, a mole is equal to 6.02 times 10 to the 23rd something, right? So if I have a mole of cars, I have 6.02 times 10 to the 23rd cars, right? If I have a mole of gas molecules, that's going to be 6.02 times 10 to the 23rd gas molecules, right? R is known as the universal gas constant. Okay. R is known as the universal gas constant, and that is equal to 8.31 joules per mole Kelvin. Okay. So 8.31 joules per mole Kelvin. Okay. And then we have our temperature. Okay. Temperature is T, right? It's pretty self-explanatory. T is temperature. I should tell you, though, that it is the temperature in Kelvin, okay? And my pen's not wanting to work. Is the temperature in Kelvin, right? So not Celsius, not Fahrenheit, but Kelvin, okay? So temperature in Kelvin. All right, and then let's look at V, which is volume, okay? V is volume. Okay, usually that's going to be in meters cubed, right? So we're going to use meters cubed for our volume. And so, and finally we have P, which is pressure. Okay, so pressure we measure in pascals or kilopascals, right? Okay, so that's how you use the ideal gas equation if you know the number of moles of gas. But let's say you're just given the number of particles, right? Well, it's pretty much the same equation. You're going to use, P and then volume again, and then equal sign, of course. Now this time, though, instead of the letter N, okay, instead of the letter N, which is the number of moles of gas, you're going to use the letter, the capital letter N. So capital N, in this case, is going to be the number of molecules or number of particles of gas, okay? So instead of little n, it's going to be big N, and then instead of R this time, you're going to use Boltzmann's constant, right? So if you remember Boltzmann's constant, that was what we discussed earlier. Boltzmann's constant is that Kb number. So where's my, there it is, okay. So Boltzmann's constant is K sub B. And then if you don't remember from the previous video, it is just 1.38 times 10 to the negative 23rd joules per Kelvin. Okay, so that is Boltzmann's constant, and so that would just be NK B, and then times temperature. Okay, again in Kelvin. Okay, so that one doesn't really change. Yeah, that is not working. So temperature. Okay, all right, and those are the two forms of the ideal gas law. So you have PV equals nRT. This is the one you're going to see the most often, and this is the one that uses moles. Okay, and then you have PV equals big N KT, right? And that's using the number of particles of gas. All right, so let's look at an example problem using the ideal gas law. So we're going to use this problem here, so go and read it. We have an ideal gas at 20 degrees Celsius and a pressure of 1.5 times 10 to the 5th pascals in a 1 liter container, and we want to determine the number of moles of gas in the container. And then in part B, the gas pushes against a piston, expanding it to twice its original volume, while the pressure falls to atmospheric pressure, and it wants us to find the final temperature. So let's go ahead and look at part A. And for part A, we know that our temperature is equal to 20 degrees Celsius, okay? And so if we're going to need to convert that into Kelvin, but for right now, we'll just write it like that until we get all our knowns. And we know that the pressure, okay, is equal to 1.5 times 10 to the 5th pascals, okay? And then the volume of our container is 1 liter, okay? So for part A, we need to determine the number of moles of gas in the container. So we're looking for the number of moles. That's going to be little n, so that's going to be what we're looking for, right? So let's just start out by converting a few things. We know that we have to use Kelvin, okay? And to convert to Kelvin from Celsius, we just add 273, okay? 273. So 20 plus 273 is equal to 293 Kelvin. My pen's working again. 293 Kelvin, okay? And then also we can convert our volume from liters into meters cubed. So let's go ahead and do that. So our volume, instead of liters, is going to be meters cubed, which is 1 liter is equal to 1 times 10 to the negative 3rd meters cubed, right? So so that's all our stuff converted. Now we can use our equation to solve our problem. So let's go ahead and write out our ideal gas equation. Okay, PV equals nRT. Okay, remember we are solving for n, right? So we just rearrange our equation here. So we just say PV, okay, divide both sides by RT. So let me rewrite that. So PV over RT is then equal to N, okay? And so now we're just going to put our numbers into our equation. So we have, let's see, our pressure is 1.5 times 10 to the fifth, okay? And then multiply that times our volume, which is 1 times 10 to the negative third, okay? Then we're going to divide that by our gas constant, our universal gas constant, which is 8.31 joules per mole Kelvin. I'm not going to write all that in there. And then multiplied by our temperature, which is 293 Kelvin. Okay, and so from there we can just put that into our calculator, right? And this is all equal to N, by the way. So it's not really okay. I'm trying to separate those two there. So let's go ahead and put that in our calculator. All right. So if you have a graphing calculator, it's pretty handy. But if not, you can totally still do that. So 1.5 times 10 to the fifth, and then multiply that times 1 times 10 to the negative third. Oh, forgot my parentheses there. Okay, and then let's go ahead and there we go. And divide all that. So divide by 8.31 times 293, and we get 0.06 moles. Okay, so 0.06 moles. Or you could say 6.16 times 10 to the negative second. Either way is up to you. So N is equal to 6.16 times 10 to the negative second moles. Okay, and that's the number of moles we have in our gas, or the moles of gas molecules, I guess. All right, so now let's look at part B. Okay, so part B wants us to find something a little bit different. It wants us to find the final temperature if our gas pushes against a piston and expands to twice its original volume, while the pressure falls to atmospheric pressure. So what we need to do is we need to look at, let's go ahead and bring that down a bit. Okay. So let's go ahead and write out what we know. We know that we have two states here. We have our final state, okay, which is going to be, let's just write that as P final, V final is equal to N, which is not going to change. The number of moles is not going to change. R is not going to change either, right? That's the universal gas constant. T final, okay, so PFVF is equal to NRTF, right? So PV and T are the three things that can change. The number of moles and the universal gas constant are not going to change, okay? We're still in an enclosed container, so we're not adding or subtracting any gas molecules. And then what we can do is that we can divide this final state by the initial state. So we can say that, we can set up like a ratio here. So we can say that P initial, V initial is equal to N R T initial, okay? And then so what happens then is we can cancel out, right? We can cancel out N and R, and we get P final, V final divided by P1, V1 is equal to T final over T initial, okay? So now we should be able to solve now for T final, right? So that's what we're looking for. We're looking for T final here. So let's go ahead and let's go ahead and write out what we know and what we don't know. So we know that our T initial was equal to 293 Kelvin, right? We also know that our V initial was equal to 1 liter, okay, or 1 times 10 to the third, negative third rather, meters cubed, okay. And let's see what else. We also know that our V final, okay, I'm sorry, I forgot about pressure. We also know that our pressure initial is, was equal to 1.5 times 10 to the 5th pascals, okay? Now let's look at our, we don't know what T final is, that's what we're looking for, but we know that V final is equal to, it's atmospheric pressure, so it's going to be 1 times 10 to the 5th pascals, okay, or 1.1, it's roughly this, 1.01 rather, it's roughly the same. And then we also know that our, I'm sorry, that's pressure final. That's my bad. Okay. And then we also know that our V final, I should say, V final is equal to 2 liters or 2 times 10 to the negative 3rd meters cubed. Although for this one, you can leave it in liters because you'll see why here in a moment. And then that's our V final. And so now we can solve for T final. That's going to be our solve thing, right? The thing we're solving for. So to solve for T final, okay, we're just going to use this up here. And all you really need to do is multiply both sides of the equation by T initial. So I can just say that P F VF divided by P initial V initial times T initial is equal to T final, okay? And then from there we just put our numbers into the equation, right? So our P final here was 1 times 10 to the 5th, right? Pascals, okay? Multiplied by V final, which you can leave it as 2 liters or you can write it in as 2 times 10 to the negative 3rd. The reason you can do that is because really we're just looking at the ratio between V final and V initial, and it's going to be the same, so it really doesn't matter. So I'm just going to write in 2 liters here. Okay, so 2 liters, and then divide that by our P initial, which is 1.5 times 10 to the 5th. Okay, and then multiply that times 1 liter. Okay, that's our V initial. And so we do that, and we put it into our calculator, okay, and we get, okay, and so we say, let's see, 1.5, or 1 rather, times 10 to the 5th, times 2, okay, and we divide that by 1.5 times 10 to the 5th, okay. Hold on. 1.5 times 10 to the 5th. And then just 1, actually. I don't know why I did that. Okay. Like that. Okay, and you get 1.3 as our, which doesn't make any sense. Oh, yeah. Okay, 1.3, and then we multiply that times, I forgot the last step, which is multiplying by 293. Okay, so yeah, I made a mistake there. So 293. Okay. Okay, and we get our answer, which is 390 point, you can say 391 Kelvin. Okay, so our answer was 391 Kelvin. All right, so just a quick recap there. Okay, all we did was we had an initial state and a final state, and we found the ratio between those two. We said that we could set up a ratio there, and so we'd use that to find our equation. Okay, we just solved that to find our equation. Then we put our numbers in the equation, and then I forgot to put the temperature in there and multiply it, which is why I had that confusion at first. But then we remembered that I did need to multiply it by our initial temperature, and we got 391 Kelvin. Okay. So, one thing to remember is if it doesn't look right, if it doesn't make sense, like if you remember, I got like 1.3, it didn't make sense, right? So we had to go back and consider maybe that we missed something, and it turns out we did. We forgot to multiply that initial temperature. All right, so that's an example of the ideal gas law. Thanks for watching.